Chapter 43, Log-Structured File Systems. In the early 90s, a group at Berkeley led by Professor John Osterhout and graduate student Mendel Rosenblum developed a new file system known as the log-structured file system. Their motivation to do so is based on the following observations. System memories are growing. As memory gets bigger, more data can be cached in memory. As more data is cached, disk traffic increasingly consists of writes as reads are serviced by the cache. Thus, file system performance is largely determined by its write performance. There is a large gap between random I/O performance and sequential I/O performance. Hard drive transfer bandwidth has increased a great deal over the years. As more bits are packed into the surface of a drive, the bandwidth when accessing said bits increases. Seek and rotational delay costs, however, have decreased slowly. It is challenging to make cheap and small motors spin the platters faster or move the disk arm more quickly. Thus, if you are able to use disks in a sequential manner, you gain a sizable performance advantage over approaches that cause seeks and rotations. Existing file systems perform poorly on many common workloads. For example, FFS would perform a large number of writes to create a new file of size 1 block. One for a new inode, one to update the inode bitmap, one to the directory data block the file is in, one to the directory inode to update it, one to the new data block that is a part of the new file, and one to the data bitmap to mark the data block as allocated. Thus, although FFS places all of these blocks within the same block group, FFS incurs many short seeks and subsequent rotational delays, and thus performance falls far short of peak sequential bandwidth. File systems are not RAID aware. For example, both RAID 4 and RAID 5 have the small write problem, where a logical write to a single block causes 4 physical I/Os to take place. Existing file systems do not try to avoid this worst-case RAID writing behavior. Tip: details matter. All interesting systems are comprised of a few general ideas and a number of details. Sometimes when you are learning about these systems, you think to yourself, oh, I get the general idea, the rest is just details, and you only half learn how things really work. Don't do this. Many times these details are crucial. As we'll see with LFS, the general idea is easy to understand, but to really build a working system, you have to think through all of the tricky cases. An ideal file system would thus focus on write performance and try to make use of sequential bandwidth on the disk. Further, it would perform well on common workloads that not only write out data, but also update on-disk metadata structures frequently. Finally, it would work well on RAIDs, as well as single disks. The new type of file system Rosenblum and Osterhout introduced was called LFS, short for the log-structured file system. When writing to disk, LFS first buffers all updates, including metadata, in an in-memory segment. When the segment is full, it is written to disk in one long sequential transfer to an unused part of the disk. LFS never overwrites existing data, but rather always writes segments to free locations. Because segments are large, the disk, or RAID, is used efficiently, and performance on the file system approaches its zenith. Writing to the disk sequentially. We thus have our first challenge. How do we transfer all updates to file system state into a series of sequential writes to disk? To understand this better, let's use a simple example. Imagine we are writing a data block D to a file. Writing the data block to disk might result in the following on-disk layout with D written at disk address A0. However, when a user writes a data block, it is not only data that gets written to disk. There is also other metadata that needs to be updated. In this case, let's also write the inode I of the file to disk and have it point to the data block D. When written to disk, the data block and inode would look something like this. Note that the inode looks as big as the data block, which generally isn't the case. In most systems, data blocks are 4 KB in size, whereas an inode is much smaller, around 128 bytes. This basic idea of simply writing all updates, such as data blocks, inodes, etc., to the disk sequentially sits at the heart of LFS. If you understand this, you get the basic idea. But As with all complicated systems, the devil is in the details. 43.2. Writing sequentially and effectively. Unfortunately, writing to disk sequentially is not alone enough to guarantee efficient writes. For example, imagine if we wrote a single block to address A at time t. We then wait a little while and write to the disk at address A plus 1. The next block address in sequential order, but at time t plus delta. In between the first and second writes, unfortunately, the disk is rotated. When you issue the second write, it will thus wait for most of a rotation before being committed. Specifically, if the rotation takes time t rotation, the disk will wait t rotation minus delta before it can commit the second write to the disk surface. And thus you can hopefully see that simply writing to disk in sequential order is not enough to achieve peak performance. Rather, you must issue a large number of contiguous writes, or one large write, to the drive in order to achieve good write performance. To achieve this end, LFS uses an ancient technique known as write buffering. Before writing to the disk, LFS keeps track of updates in memory. When it has received a sufficient number of updates, it writes them to disk all at once, thus ensuring efficient use of the disk. The large chunk of updates LFS writes at one time is referred to by the name of a segment. Although this term is overused in computer systems, here it just means the largest chunk, which LFS uses to group writes. Thus, when writing to disk, LFS buffers updates in an in-memory segment, and then writes the segment all at once to the disk. As long as the segment is large enough, these writes will be efficient. Here's an example in which LFS buffers two sets of updates into a small segment. Actual segments are larger, a few MB. The first update is of 4 block writes to file J. The second is 1 block being added to file K. LFS then commits the entire segment of 7 blocks to the disk at once. The resulting on-disk layout of these blocks is as follows. (43.3) How much to buffer? This raises the following question. How many updates should LFS buffer before writing to disk? The answer, of course, depends on the disk itself, specifically how high the positioning overhead is in comparison to the transfer rate. See the FFS chapter for a similar analysis. For example, assume that positioning, i.e. rotation and seek overheads, before each write takes roughly t position seconds. Assume further that the disk transfer rate is r peak MB per second. How much should LFS buffer before writing when running on such a disk? The way to think about this is that every time you write, you pay a fixed overhead of the positioning cost. Thus, how much do you have to write in order to amortize that cost? The more you write, the better, and the closer you get to achieving peak bandwidth. To obtain a concrete answer, let's assume we are writing out d MB. The time to write out this chunk of data, t write, is the positioning time, t position, plus the time to transfer d over r peak, or t write equals t position plus d over r peak. And thus the effective rate of writing, r effective, which is just the amount of data written divided by the total time to write it, is r effective equals d over t write equals d over t position plus d over r peak. What we're interested in is getting the effective rate, r effective, close to the peak rate. Specifically, if we want the effective range to be some fraction f of the peak rate, where 0 is less than f is less than 1. A typical f might be 0.9 or 90% of the peak rate. In mathematical form, this means we want r effective equals f times r peak. At this point, we can solve for d. R effective equals d over t position plus d over r peak equals f times r peak. D equals f times r peak times t position plus d over r peak. D equals f times r peak times t position plus f times r peak times d over r peak. D equals f over 1 minus f times r peak times t position. Let's do an example with a disk of positioning time of 10 milliseconds and a peak transfer rate of 100 MB per second. Assume we want an effective bandwidth of 90% of peak, f equals 0.9. In this case, d equals 0.9 over 0.1 times 100 MB per second times 0.01 seconds equals 9 MB. Try some different values to see how much we need to buffer in order to approach peak bandwidth. How much is needed to reach 95% of peak? 99%. 43.4. Problem, finding inodes. To understand how we find an inode in LFS, let us briefly review how to find an inode in a typical Unix file system. In a typical file system such as FFS or even the old Unix file system, finding inodes is easy because they are organized in an array and placed on disk at fixed locations. For example, the old Unix file system keeps all inodes at a fixed portion of the disk. Thus, given an inode number and the start address to find a particular inode, you can calculate its exact disk address by simply multiplying the inode number by the size of an inode and adding that to the start address of the on-disk array. Array-based indexing, given an inode number, is fast and straightforward. Finding an inode given an inode number in FFS is only slightly more complicated, because FFS splits up the inode table into chunks and places a group of inodes within each cylinder group. Thus, one must know how big each chunk of inodes is and the start addresses of each. After that, the calculations are similar and also easy. In LFS, life is more difficult. Why? Well, we've managed to scatter the inodes all throughout the disk. Worse, we never overwrite in place, and thus the latest version of an inode, i.e. the one we want, keeps moving. 43.5. Solution through indirection. The inode map. To remedy this, the designers of LFS introduced a level of indirection between inode numbers and the inodes through a data structure called the inode map, IMAP. The IMAP is a structure that takes an inode number as input and produces the disk address of the most recent version of the inode. Thus, you can imagine it would often be implemented as a simple array with 4 bytes, a disk pointer per entry. Any time an inode is written to disk, the IMAP is updated with its new location. The IMAP, unfortunately, needs to be kept persistent, i.e. written to disk. Doing so allows LFS to keep track of the locations of inodes across crashes, and thus operate as desired. Thus, a question, where should the IMAP reside on the disk? It could live on a fixed part of the disk, of course. Unfortunately, as it gets updated frequently, this would then require updates to file structures to be followed by writes to the IMAP, and hence performance would suffer, i.e. there would be more disk seeks between each update and the fixed location of the IMAP. Instead, LFS places chunks of the inode map right next to where it is writing all of the other new information. Thus, when appending a data block to file K, LFS actually writes the new data block, its inode, and a piece of the inode map all together on the disk as follows. In this picture, the piece of the IMAP array stored in the block marked IMAP tells LFS that the inode K is at disk address A1. This inode, in turn, tells LFS that its dated block D is at address A0. .6. Completing the solution, the checkpoint region. The clever reader might have noticed a problem here. How do we find the inode map now that pieces of it are also all spread across the disk? In the end, there is no magic. The file system must have some fixed and known location on disk to begin a file lookup. LFS has just such a fixed place on disk for this, known as the checkpoint region, CR. The checkpoint region contains pointers to, i.e. addresses of, the latest pieces of the inode map, and thus the inode map pieces can be found by reading the CR first. Note the checkpoint region is only updated periodically, say every 30 seconds or so, and thus performance is not ill-affected. Thus, the overall structure of the on-disk layout contains a checkpoint region, which points to the latest pieces of the inode map. The inode map pieces which contain addresses of the inodes, The inodes point to files and directories just like typical Unix file systems. Here's an example of the checkpoint region. Note it is all the way at the beginning of the disk at addresses 0, and a single IMAP chunk, inode, and data block. A real file system would of course have a much bigger CR. Indeed, it would have 2, as we'll come to understand later. Many IMAP chunks, and of course many more inodes, data blocks, etc. Reading a file from disk, a recap. To make sure you understand how LFS works, let us now walk through what must happen to read a file from disk. Assume we have nothing in memory to begin. The first on-disk data structure we have read is the checkpoint region. The checkpoint region contains pointers, i.e. disk addresses, to the entire inode map, and thus LFS then reads the entire inode map and caches it in memory. After this point, when given an inode number of a file, LFS simply looks up the inode number to inode disk addresses mapping in the IMAP and reads the most recent version of the inode. To read a block from the file at this point, LFS proceeds exactly as a typical Unix file system, by using direct pointers or indirect pointers, or doubly indirect pointers as need be. In the common case, LFS should perform the same number of IOs as a typical file system when reading a file from disk. The entire IMAP is cached, and thus the extra work LFS does during a read is to look up the inode's address in the IMAP. 43.8. What about directories? Thus far, we've simplified our discussion a bit by only considering inodes and data blocks. However, to access a file in a file system, such as /home/remzi/foo, one of our favorite fake file names, some directories must be accessed too. So how does LFS store directory data? Fortunately, directory structure is basically identical to classic Unix file system, in that a directory is just a collection of name inode number mappings. For example, when creating a file on disk, LFS must both write a new inode some data as well as the directory data in its inode that refer to this file. Remember that LFS will do so sequentially on the disk after buffering the updates for some time. Thus, creating a file foo in a directory would lead to the following new structures on disk. The piece of the inode map contains the information for the location of both the directory file dir as well as the newly created file f. Thus, when accessing file foo with inode number k, you would first look in the inode map, usually cached in memory, to find the location of the inode of directory dir, a3. You then read the directory inode, which gives you the location of the directory data, a2. Reading this data block gives you the name to inode number mapping of foo k. You then consult the inode map again to find the location of inode number k, a1, and finally read the desired data block at address a0. There's one other serious problem in LFS that the inode map solves, known as the recursive update problem. The problem arises in any file system that never updates in place, such as LFS, but rather moves updates to new locations on the disk. Specifically, whenever an inode is updated, its location on disk changes. If we hadn't been careful, this would have also entailed an update to the directory that points to this file, which then would have mandated a change to the parent of that directory, and so on, all the way up the file system tree. LFS cleverly avoids this problem with the inode map. Even though the location of an inode may change, the change is never reflected in the directory itself. Rather, the IMAP structure is updated, while the directory holds the same name to inode number mapping. Thus, through indirection, LFS avoids the recursive update problem. 43.9. A new problem, garbage collection. You may have noticed another problem with LFS. It repeatedly writes the disk, the latest version of a file, to new locations on disk. This process, while keeping writes efficient, implies that LFS leaves old versions of file structures scattered throughout the disk. we rather unceremoniously call these old versions garbage. For example, let's imagine the case where we have an existing file referred to by inode number k, which points to a single data block D0. We now update that block, generating both a new inode and new data block. The resulting on-disk layout of LFS would look something like this. Note, we omit the IMAP and other structures for simplicity. A new chunk of IMAP would also have to be written to disk to point to the new inode. In the diagram, you can see that both the inode and data block have two versions on disk, one old, the one on the left, and one current and thus live, the one on the right. By the simple act of logically updating a data block, a number of new structures must be persisted by LFS, thus leaving old versions of said blocks on the disk. As another example, imagine we append a block to that original file K. In this case, a new version of the inode is generated, but the old data block is still pointed to by the inode. Thus, it is still live and very much part of the current file system. So what should we do with these older versions of inodes, data blocks, and so forth? One could keep these older versions around and allow users to restore old file versions. For example, when they accidentally overwrite or delete a file, it could be quite handy to do so. Such a file system is known as a versioning file system because it keeps track of the different versions of a file. However, LFS instead keeps only the latest live version of a file. Thus, in the background, LFS must periodically find these old dead versions of file data, inodes, and other structures and clean them. Cleaning should thus make blocks on disk free again and able to be used for subsequent writes. Note that the process of cleaning is a form of garbage collection, a technique that arises in programming languages that automatically free unused memory for programs. Earlier, we discussed segments. As important as they are, the mechanism that enables large writes to disk in LFS. As it turns out, they're also quite integral to effective cleaning. Imagine what would happen if the LFS cleaner simply went through and freed single data blocks, inodes, etc. during cleaning. The result is a file system with some number of free holes mixed between allocated space on disk. Write performance would drop considerably, as LFS would not be able to find a large contiguous region to write to disk sequentially and with high performance. Instead, the LFS cleaner works on a segment-by-segment basis, thus clearing up large chunks of space for subsequent writing. The basic cleaning process works as follows. Periodically, the LFS cleaner reads in a number of old, partially used segments, determines which blocks are live within these segments, and then write out a new set of segments with just the live blocks within them, freeing up the old ones for writing. Specifically, we expect the cleaner to read in M existing segments, compact their contents into N new segments, where N is less than M, and then write the N segments to disk in new locations. The old M segments are then freed and can be used by the file system for subsequent writes. We are now left with two problems, however. The first is mechanism. How can LFS tell which blocks within a segment are live and which are dead? The second is policy. How often should the cleaner run and which segments should it pick to clean? 43.10. Determining block liveness. We address the mechanism first. Given a data block D within a non-disk segment S, LFS must be able to determine whether D is live. To do so, LFS adds a little extra information to each segment that describes each block. Specifically, LFS includes, for each data block D, its inode number, which file it belongs to, and its offset, which block of the file this is. This information is recorded in a structure at the head of the segment known as the segment summary block. Given this information, it is straightforward to determine whether a block is live or dead. For a block D located on disk at address A, look in the segment summary block and find its inode number N and offset T. Next, look in the IMAP to find where N lives and read N from disk. Perhaps it is already in the memory, which is even better. Finally, using the offset T, look in the inode or some indirect block to see where the inode thinks the Tth block of this file is on disk. If it points exactly to disk address A, LFS can conclude that the block D is live. If it points anywhere else, LFS can conclude that D is not in use, i.e. it is dead, and thus know that this version is no longer needed. Here is a pseudocode summary. NT equals segment summary A. inode equals read IMAP N. If inode T equals A, block D is alive, else block D is garbage. Here is a diagram depicting the mechanism in which the segment summary block marked SS records that the data block at address A0 is actually a part of file K at offset 0. By checking the IMAP for K, you can find the inode and see that it does indeed point to that location. There are some shortcuts LFS takes to make the process of determining live lists more efficient. For example, when a file is truncated or deleted, LFS increases its version number and records the new version number in the IMAP. By also recording the version number on the on-disk segment, LFS can short-circuit the longer check described above by simply comparing the on-disk version number with the version number in the IMAP, thus avoiding extra reads. 43.11, a policy question. Which blocks to clean and when? On top of the mechanism described above, LFS must include a set of policies to determine both when to clean and which blocks are worth cleaning. Determining when to clean is easier, either periodically during idle time or when you have to because the disk is full. Determining which blocks to clean is more challenging and has been the subject of many research papers. In the original LFS paper, the authors describe an approach which tries to segregate hot and cold segments. A hot segment is one in which the contents are being frequently overwritten. Thus, for a segment, the best policy is to wait a long time before cleaning it, as more and more blocks are getting overwritten in new segments and thus being freed for use. A cold segment, in contrast, may have few dead blocks, but the rest of its contents are relatively stable. Thus, the authors conclude that one should clean cold segments sooner and hot segments later, and develop a heuristic that does exactly that. However, as with most policies, this policy isn't perfect. Later approaches show how to do better. 43.12, crash recovery in the log. One final problem. What happens if the system crashes while LFS is writing to disk? As you may recall in the previous chapter about journaling, crashes during updates are tricky for file systems and thus something LFS must consider as well. During normal operation, LFS buffers writes in a segment and then, when the segment is full or when some amount of time has elapsed, writes the segment to disk. LFS organizes these writes in a log, i.e. the checkpoint region points to a head and tail segment, and each segment points to the next segment to be written. LFS also periodically updates the checkpoint region. Crashes could clearly happen during either of these operations, write to a segment, write to the CR. So how does LFS handle crashes during writes to these structures? Let's cover the second case first. To ensure that the CR update happens atomically, LFS actually keeps two CRs, one at either end of the disk, and writes to them alternately. LFS also implements a careful protocol when updating the CR with the latest pointers to the inode map and other information. Specifically, it first writes out a header with timestamp, then the body of the CR, and then finally one last block, also with a timestamp. If the system crashes during a CR update, LFS can detect this by seeing an inconsistent pair of timestamps. LFS will always choose to use the most recent CR that has consistent timestamps, and thus consistent update of the CR is achieved. Let's now address this first case. Because LFS writes the CR every 30 seconds or so, the last consistent snapshot of the file system may be quite old. Thus, upon reboot, LFS can easily recover by simply reading in the checkpoint region the IMAP pieces it points to, and subsequent files and directories. However, the last many seconds of updates would be lost. To improve upon this, LFS tries to rebuild many of those segments through a technique known as roll forward in the database community. The basic idea is to start with the last checkpoint region, find the end of the log which is included in the CR, and then use that to read through the next segments and see if there are any valid updates within it. If there are, LFS updates the file system accordingly and thus recovers much of the data and metadata written since the last checkpoint. See Rosenblum's award-winning dissertation for details. 43.13 Summary. LFS introduces a new approach to updating the disk. Instead of overwriting files in places, LFS always writes to an unused portion of the disk, and then later reclaims that old space through cleaning. This approach, which in database systems is called shadow paging, and in file system speak is sometimes called copy on write, enables highly efficient writing, as LFS can gather all updates into an in-memory segment and then write them out together sequentially. The large writes that LFS generates are excellent for performance on many different devices. On hard drives, large writes ensure that positioning time is minimized. On parity-based RAID, such as RAID 4 and RAID 5, they avoid the small write problem entirely. Recent research has even shown that large IOs are required for high performance on flash-based SSDs. Thus, perhaps surprisingly, LFS-style file systems may be an excellent choice, even for these new mediums. The downside to this approach is that it generates garbage. Old copies of the data are scattered throughout the disk, and if one wants to reclaim such space for subsequent usage, one must clean old segments periodically. Cleaning became the focus of much controversy in LFS, and concerns over cleaning costs perhaps limited LFS's initial impact on the field. However, some modern commercial file systems, including NetApp's Waffle, Sun's ZFS, and Linux, BTRFS, and even modern flash-based SSDs, adopt a similar copy-on-write approach to writing on disk, and thus the intellectual legacy of LFS lives on in these modern file systems. In particular, Waffle got around cleaning problems by turning them into a feature. By providing old versions of the file system via snapshots, users could access old files whenever they deleted current ones accidentally.